Hello and welcome to section 1.4 on rates of change. In this section, we will discuss averages. Specifically, average rates of change, average velocity, and secant lines. Wait a second, what is a secant line and how is it connected to averages? Given a function f of x, a secant line is a line which passes between 2 points on the graph. As a line is fixed, once 2 points are specified, there can only be one secant line for 2 points a f of a and b f of b. What is the slope of a secant line? As the secant line passes between the 2 points, we can calculate the slope by taking the rise over run. That is b's y value minus a's y value, the rise, dividing by the difference of b and a. The slope equation for a secant line is known as an average rate of change. A rate of change is a measure of how input changes affect output changes. Take for example the parabola y equals x squared. Say we are interested in finding the average rate of change between the values -1 and 2. We would use our equation for the average rate of change, letting a be -1 and b be 2. As -1 squared is 1 and 2 squared is 4, we calculate the average rate of change as 1. Keep in mind, the slope of the secant line is the average rate of change, so we can find the equation of the secant line using the point-slope formula. We've now connected secant lines to an average, but why does the word average appear in the average rate of change? We can best answer this with an example. Suppose s represents the height of a ball, in feet, once it has been launched at time 0. The function has input t in seconds and output s in feet. Let's calculate the heights at times 0, 1, and 2 seconds after the ball has been thrown. Plugging these time values into the s function yields heights of 0, 64, and 96 feet. The average rate of change for s between 1 and 2 is 32. This number represents the average change in feet that the ball moves during the first second. If we calculate the rate of change between 0 and 2, we obtain 48 feet per second. Notice that the ball only moves 96 feet in the first 2 seconds, 32 of which happen after the first second. The velocity of the ball is not constant. We are reporting the average velocity of the ball, not the velocity instant to instant. The same is true for general functions. The average rate of change records what it says, the average change in y per x unit over a certain x interval. The distance function s of t will commonly be used to represent the position of an object as a function of time. The units for s will be distance measurements, like inches, feet, meters, and miles. When we find the average rate of change for the distance function s of t, we are dividing distance by time. These rates of change have units distance per time, commonly known as velocity. Take for example miles per hour, feet per second. Challenge yourself. Pause the video and calculate the average rate of change on the interval -1 to 1 and the interval 0 to 2 for the functions f and g shown. Let's start with the line f. Using our equation for a rate of change, we obtain 1 in part 1 and 1 in part 2. This should make sense as a line is special. It has a constant rate of change. Turning to the cubic function g, we use the equation for average rate of change to obtain the values 1 and 4. Notice that g does not have a constant rate of change. This is a fact which can be visualized through secant lines. The black line has slope 1 and is the secant line for the x values -1 and 1 on the graph. The red line has slope 4 and is the secant line for the x values 0 and 2 on the graph. To summarize this introduction, we are working with averages. Keep in mind that the slope of the secant line is an average rate of change, and that velocity is an example of a rate of change. You've seen the basics. Now work towards mastery through practice and study.